Okay, how did you make out with using your properties of logarithms? In number 23, we're asked to evaluate or simplify log of 10 raised to the 14th power. And you should be able to identify that is a case of property number 3, right? Because we have the invisible 10 here as the base. This is a common log. Property 3 says that when the base of the log equals the base of the exponential expression, the answer is just the exponent, 14. Over here, what property is at play there? Notice, common logarithm, they give you a little hint. They actually showed the 10 there. They didn't need to do that. But you see that the base of this log is equal to the base that this log value is the exponent of. This is all one big exponent up here. So this one, number 4, talks about exponents, and it does require that the base of the log equals the base of the overall expression. So we have that, 10, 10. So the answer is just this number 12 that we're taking the log of here. 12. Okay. Let's look at some additional properties. Properties 6, 7, and 8 on page 336. Again, for positive constants b, where b is not equal to 1, k is a real number, m and n are positive numbers. These 3 important statements are true. The log of 2 quantities multiplied together to the base b is equal to the log of the first quantity base b plus the log of the second quantity base b. And again, that is why Napier invented logs, because it's much easier to add up these 2 numbers than to multiply these 2 big numbers here. So, you might wonder, what about division? Looks just like this, except it's subtraction. You subtract the log of the denominator, and I need to put my bases in there. Right? It's not log base 10, it's log base b. So the difference is you're subtracting here, whereas in this case you were adding. And the log of the denominator is being subtracted from the log of the numerator. Finally, this one comes in handy all the time. If you have some quantity m to the power k, and you want to take the log of that, if you feel like it, you could just move that k outside just like that. That is a true fact. All right, let's make use of these in example 10, which is about rewriting logs. In part A, we have the log base 4 of 2 quantities being added to each other. It's 5 times the binomial x minus 7. Okay. I see 5 is playing the role of the big M here. X minus 7 is playing the role of the n. So if I apply this property, that's true, right? That's how I break it up into an addition problem. I'll underline that as my final answer. There's nothing more that can be done with that. In part B, the natural log of the quantity e squared times e plus 3. So there's even more going on here. I've got an exponential quantity in here. Furthermore, it's part of a multiplication problem in there. So the first thing to do is to apply our rule for multiplication, and we'll deal with that exponent next. Okay, e plus 3 plays the role of n, e squared plays the role of m. So I break it up like that. Now, there's nothing I can do over here. We're stuck there, we're finished. But here I have the log of something raised to a power. If I want, I can use that property. Furthermore, this is the log of e to the base e, right? That's what natural log means. So it's case 1 there. This is just a strange way of writing 1. And there's my finished answer. By the way, instead of going like this, you could have also looked at this and said, oh, that's an example of property 3. Log base n, log base e of e raised to a power. I could have immediately gone to the 2 like that. So you see how all these rules fit together consistently. They all make sense. You're not going to have contradictions depending on how you apply the rules. This is a consistent system of rules for doing calculations. In part C, we have a division going on. I have the common log of x minus 8 over x. So this is a perfect example of property number 7. This is equal to the common log of x minus 8 minus the common log of x. And there's nothing more that could be done to simplify it after that. Part D, the log base 4 of y to the power 6. The base of the exponential expression is y. The base of the log is 4, so they're different. They're not the same. We can't apply that rule. However, it does match up with 8, property 8. And I can move that 6 outside and write the expression like that if I want to, if that helps me. Finally, let's go to part E. The natural log of 1 over x to the 5th. How can we simplify this? Well, it's a division problem. So the log of two things being divided is the difference of their logs. This is applying rule number 7. Now the log of 1 is always 0. That's property number 2. And in fact, I can use property 8 to get rid of that exponent there. That's always available to me. So I would end up there. Now some of you might notice there's a different way to do this. You might say, hey, why didn't you just convert this fraction to exponential form? All right. That's true, right? Now I can just go ahead and use property 8 and get that exponent on the outside. And of course, no matter which